If you spend any time on tech social media, you have seen the posts. Someone types a single plain English prompt into an AI, and seconds later, they are playing a fully custom video game. The most prominent examples show complex Mario 64-style 3D platformers running right in the browser. The implication is that anyone can bypass years of software engineering and speak a game into existence. The promised result looks incredible. You get a functional, stylized environment, complete with animated characters, smooth physics, and a camera that reliably follows the action. But paste that exact same prompt into a one-shot AI generator, and you get a wildly spinning, chaotic mess clipping violently through the floor. Look at these two outcomes side by side in this comparison matrix. On the left, we have the viral promise of a polished game. On the right, the broken logic of the one-shot reality. The gap between these two columns is immense. You cannot actually play the version on the right. The collision detection fails, the spatial logic collapses, and the controls are completely unresponsive. This gap exists because those viral posts omit the days of manual iteration, debugging, and traditional coding expertise required to get the final result. Chasing the myth of a one-shot 3D masterpiece leads to wasted hours fighting the tool instead of making a game. There is a vast difference between asking an AI to build a game in a single prompt and using it as a co-pilot for iterative development. For that viral Mario-style browser game, the creator spent days refining the code using libraries like 3.js and feeding errors back into the AI to slowly build up the mechanics. Large language models also cannot generate custom 3D models out of thin air. You must integrate external AI asset generators to get those great-looking characters and environments. Tools like Meshi or Tripo take 2D image generations and convert them into actual 3D meshes that your code can import and render. In a functional workflow, the language model serves as a code assembler, generating the glue logic needed to connect disparate 3D assets. Because the AI inevitably makes structural mistakes, you need a baseline understanding of 3D coding concepts. You must fix lighting, adjust camera matrices, and correct physics calculations when the model hallucinates. These viral projects demonstrate traditional game development workflows accelerated by AI assistance. To test the actual baseline capabilities of these models, we ran a controlled experiment. We fed the exact same one-shot 3D platformer prompt into 5 top-tier language models to see what they produce without human intervention. Here is our diagnostic scorecard. We evaluate Claude, OnSpace, Lovable, ChatGPT, and Gemini across 3 categories: visual styling, 3D spatial logic, and frame rate. Claude 4.6 and OnSpace receive failing grades for spatial logic. Both models fail to establish or maintain a consistent camera direction within the 3D space. Without a functional camera, the player gets disoriented immediately, turning the core game loop into a chaotic, unplayable mess. Looking at Lovable and ChatGPT 5.4 thinking, both models score highly in the visual styling column. These two successfully write the code to generate stylized worlds, complete with dynamic shadows and recognizable characters. However, they struggle with surface normals. In ChatGPT's generation, you can see a spherical map where the palm trees grow perfectly vertical in world coordinates, rather than pointing outward from the sphere's surface. Current reasoning models prioritize visual aesthetics, but they still stumble on the precise vector math required to build a functional 3D space. That leaves us with the final model in our test, Gemini 3.1 Pro. Out of all the options, it is the only tool that actually understands the physical environment. Looking at the updated scorecard for Gemini, we see a passing grade for 3D spatial logic, but a severe failing grade in frame rate and usability. Gemini successfully solves the geometry puzzle. The world makes sense, the camera tracks the character properly, and the core game loop functions. But that structural accuracy comes with a massive trade-off. The code it generates is so unoptimized that the frame rate plummets. This is a performance bottleneck. The math is valid, but the execution is so inefficient that the computer struggles to render the frames, making the game functionally unplayable. To fix this, a developer has to step in, manually debug the output, and rewrite the rendering loops to recover that performance. Relying entirely on a one-shot generation currently forces a choice between a visually stunning world with broken math or a logically sound game that runs too slowly to play. How you use these tools depends heavily on your existing coding experience. We can map out a strategy using this decision tree. Starting at the top, ask yourself, is your goal a zero-code instant game or accelerated prototyping? If you have no coding experience and want a ready-to-play 3D game with a single prompt, follow the path on the left. This path terminates at a hard stop. You will hit a wall dealing with hallucinated game physics and broken cameras. If you are an absolute beginner, lower your scope and pivot. Build 2D text adventures or puzzle games where AI is less likely to break logic. If you already know your way around libraries like 3.js, you fall into the pragmatic prototyper path. By treating models strictly as a foundational starting point, you can skip the boilerplate code and gain a 20 to 30% boost in your prototyping speed. One-shot 3D vibe coding is currently a social media myth. However, treating AI as a manual code developer offers a measurable speed advantage for those willing to do the work.